Section 12.6, graphing quadric, not quadratic, but quadric surfaces. Quadric surfaces are second-degree polynomials in three variables, namely x and y and z, and they are like counterparts of what? Conic sections, which we have seen in previous like algebra classes, you know, such as parabola, ellipse, hyperbola, circle. So, for instance, sphere x squared plus y squared plus z squared equals r squared is a quadric surface. But in general, quadric surface has this long form, such as ax squared plus by squared, all the way to the constant equal to 0. So we're going to see some variation of this general form in this section, and we like to see how the graph of these kind of surfaces look like. There are like 6 of those, so we'll go over it one at a time, and hopefully by the end of this video, we will be going through all 6 quadric surfaces. If you remember from previous sections of chapter 12, cylinder is kind of the summation of 2 variables with a positive number. So in this case, the cylinder is in xz plane, right? Here's, so x is equal to what? Plus or minus 2. Z is equal to plus or minus 2. So the radius of this cylinder happens to be what? 2, and it's a circle in what? XZ plane. However, the y is missing, so what we do, we kind of stretch this along the y-axis, and lo and behold, what we got is honest to goodness what? Cylinder, as you can tell. However, I can draw the cylinder in the first octant. So all I have to do is like make sure I have the x and z intercepts, and I just stretch it, and then I close it off here. And this would be like the first octant view of the same cylinder. So that means you are looking at the 1/8 of the graph, whereas this is the full view of the cylinder. When you have linear functions in 3 variables, you know the graph is a plane. So plane is the simplest flat surface you can get your hands on. So what you do, you find the x and y and z intercepts by setting what? 2 of these variables equal to 0, 1 at a time. So for instance, if I want to know where the plane hits the x-axis, I set y and z equal to 0, and I get what? 2x equals 6, so the x-intercept is 3. Similarly, I can find the y-intercept 6, and z-intercept 3/2. So remember, this is like 0, 0, 3/2. And this is 0, 6, 0. When we have good old functions from algebra classes, their graph in 3D is called cylindrical surface. In other words, it's a cylindrical looking surface. On the floor, you and I, we both know the graph kind of looks like what? This? Let's see now. At 0, sine of 0 is 0. At pi over 2, sine of pi over 2 is 1. At pi is 0. At 3 pi over 2 is negative 1. Remember, y going this way is positive, going this way is negative. And 2 pi is 0. So on the floor, the graph looks like this, which is a curve. However, z is missing. That doesn't mean z is 0. That just means z goes from negative infinity to infinity. So if you would just stretch this along the what? Z-axis, like so, lo and behold, you have your what? Cylindrical surface, which is kind of like a baby sheet of surface. Y is equal to x squared. I think we have done this before. Let's just do it one more time. And as you know, on the floor, the graph is a curve, which is what? A parabola, correct? You remember? However, in 3-dimensional is a cylindrical surface. Cylindrical what? Surface. How does it look like? Well, z is missing. Once again, z goes from negative infinity to infinity. So if you just kind of stretch this along the z-axis, And lo and behold, you have your cylindrical surface. Do you see it? So remember, these quadric surfaces are counterparts of conic sections. You know what conic sections were. So if you would take a circular cone and cut it with a plane, you know, whether you cut it like slantly or vertically or straight horizontally, you get these shapes, namely circle, parabola, hyperbola, and ellipse. Circle, you all know it's x squared plus y squared equals r squared. So if you divide both sides by r squared, you get 1. So circle is a special case of an ellipse. Do you see it? Ellipse, the denominators are not the same. So a is not the same as b. However, if you have a is equal to ax squared plus bx plus c, that's a parabola. Hyperbola has a minus between the x squares and y squares. If x squared shows up first, the branches of the hyperbola opens along the x-axis. However, if y squared shows up first in the equation, the branches of the parabola opens what? Along the y-axis, like so. And this guy is an ellipse, which kind of looks like an oval shape. So the first quadric surface is called ellipsoid. That's how you pronounce it, ellipsoid. So this is like, soid means like, ellipse means like an ellipse, so it's like an ellipse. So the graph is no longer an oval shape, but it is kind of like football shape, okay? So basically this is how the equation looks like. X squared over a positive number, y squared, z squared over c, and guess what? They are not equal each other at the same time, correct? For instance, suppose we have been asked to graph x squared over 4 plus y squared over 9 plus z squared over what? 1 equals 1. So remember, a squared is equal to 4, b squared is 9, c squared is what? 1. So if you take the square root, a is 2, b is 3, c is 1. So what we do at this point, we find the projection of the surface on xy plane, xz plane, yz plane. So that would help us to kind of complete the graph. When I say projection, what I mean is the cross-section of what would be the intersection of the surface with xy plane. Well, it turns out it's going to be a curve. And for instance, the intersection of this surface with xy plane, you set z equal to 0, and lo and behold, you get an ellipse. So this is an ellipse. And it's also an ellipse when you take the cross section of the surface with xz plane, and the same thing is true for what? For yz plane. So in all three cases, we get what? 3 ellipses. So with that in mind, what do you say we kind of try to graph an ellipsoid? So remember, like for instance, the first guy is what? X squared over 4 plus what? Y squared over 9 equals 1, correct? So if you set y equal to 0, x would be plus or minus 2, like so. And when you set x equal to 0, y is equal to plus or minus 3, like so. You see it. So what I'm getting is this kind of like an ellipse, correct? And you can continue graphing the other ellipse. So here's one more, and here's one more inside. And lo and behold, the result is called ellipsoid. So this is like a football, correct? It's no longer a curve, but it's a surface. Do you see it? Right? The next one is called elliptic paraboloid. That's how you pronounce it, elliptic paraboloid. That just means what? One of the variables happens to have a power of 1, and it's equal to the sum of the square of the remaining variables. Like in this case, z equals, let's say, x squared plus y squared, and the denominators, of course, they have to be positive, and they're constants. If a is the same as b, then what? This elliptic paraboloid might be called what? Circular Rod Paraboloid. Let's just do a problem so you guys can see how this guy works. All right. Once again, the cross-section of the surface with YZ plane, that's like, set x equal to 0, you get this. What is the graph of that? Is a parabola. With XZ plane is a parabola as well, okay? With XY plane, it's just a point because x squared over 4 plus y squared over 9 equals 0. Only what? A point, meaning origin will satisfy this. So this is like origin. Do you see it? So if you would have graphed this, okay, so for, let's say, this guy, we get a parabola along the what? Z-axis. So this would be like what? Let's say z is equal to y squared over 9. And then we have this parabola, correct? Like so, and guess what that is? And that would be z is equal to x squared over 4. So question is, what happens if I intersects this surface with the plane z is equal to 1? Right about here, what happens? What kind of cross-section do we get? Well, if you stick 1 or for z, so you get this. Do you see it? Okay, and what is that? That's also an ellipse. So what's happening at z is equal to 1, you get an ellipse. Do you see it? And that's pretty much how an elliptic paraboloid looks like. It's like a bowl. So it's also a surface. It's not a curve, it's a surface, yes? That means it has a thickness. So that's called elliptic paraboloid. Notice because z had a power of 1, so the paraboloid opens along the what? Z-axis. If you had let's say, y over c is equal to x over a squared plus what? Z squared over b squared, then the paraboloid will open along the what? Y-axis, and so on and so forth. Okay, so the next one is called a cone. Well, cone, contrary to what? Elliptic paraboloid, on the left side, you have square of the z. It's not z to the first, but it's z squared. On the right side, you still got what? Summation of the remaining two variables. So what happens is the following. The cross-section of what? Let's say, this surface with each of the xy and xz and yz plane happens to be, believe it or not, what? These are like two intersecting lines. These are like two intersecting lines. This is like two intersecting lines on the what? XZ plane. If you set y equal to 0, you get z is equal to plus or minus what? Let's say for this example, if you set y equal to 0, z is equal to plus or minus x over 3. So along the z-axis, you get two intersecting lines which goes through 0, 0, okay? Similarly, along the what? Let's say yz plane, if you set x equal to 0, solve for z, you get z is equal to plus or minus what? Y over 2, which happens to be two intersecting lines. Therefore, what we have is the following. Let me just make sure we all see this. So there you have it. Suppose now this is one of those intersections, and imagine the other guy. I'm going to draw with what? Black one is that guy right there. Do you see it? So the question is, what would be the cross section of this surface at z is equal to +1 and z is equal to -1, meaning the planes z is equal to 1 or z is equal to -1. In other words, what's happening right here and here? Well, if you replace what? the what? Z with ±1, you get this. Okay. Because whether you replace the z with plus or -1, you always get +1. And what is the graph of this guy? As you can tell, the denominators don't match, and there is a positive. So this guy is an ellipse. So what you get is something like this over here, and something like this over here. And lo and behold, what you got is called circular what? Cone. You all see it. So this is like the lower nape, that's NAPA, and this is like the upper nape, or you could call it upper half. Incidentally, if you solve this original equation of the cone for what? Z, you get z is equal to ± square root of x squared over 9 plus what? Y squared over 4. Keep in mind the upper half of the what? Cone is positive square root of x squared plus y squared, and this is x squared over 9 plus y squared over 4. And the lower half is negative square root of x squared over 9 plus y squared over 4. So if they give you this equation alone, so all you have to do is what? Graph the upper half of a cone. Is that right? And if z is equal to 0, of course you get a point. That's why these intersecting lines cross each other at what? At the origin. So that's that's how that guy goes. Okay, the next graph is called what? Hyperboloid of one sheet. It looks like a nuclear plant. Okay, so I'm just going to go ahead and kind of show you how that guy looks like. Okay, notice all variables have what? Positive square. They have a powers of 2. But one of the variables has a coefficient of negative, one of them, right? The one which has a negative, that's where what? The hyperboloid of one sheet what? Opens along. So in this case, the sheet is going to be stretched along the what? Z-axis. If x was negative, these guys were positive, then the what? Hyperboloid of one sheet would open along the what? X-axis, and similarly along the Y-axis. So let's find the cross sections. So the cross section of the surface with xy plane, that's like what? Set z is equal to 0, we get an ellipse. With xz plane, we don't get an ellipse. This is called hyperbola. And the branches open along the x-axis. This guy is also hyperbola. And what? The branches open along the y-axis. Notice here the major axis is what? Z-axis. Here the major axis is also z-axis. So what happens is the following. Here is good old what? X and y and z-axis, correct? So you have two what? Hyperbolas. One of them looks like this. The other guy kind of looks like what? This. Okay. Kind of like this. Okay. And then, so these are the two, hyperbolas. Okay. One of them opens along the x-axis. The other guy opens along the y-axis. So pardon my graph. So that's basically a rough uh, graph of this surface. And what happens when z is equal to plus or minus 6? In other words, what happens if you go right 6 units up and 6 units down below the origin? What would happen to this guy? Well, turns out if you replace the z with what? Plus or minus 6 in the original equation, this guy right here, what you're going to end up with is x squared over 9 plus y squared over 4 is equal to 61 over 25. Which that means the intersection would be a curve, and those are ellipses. So we have an ellipse here, okay, and we have an ellipse here, okay, and as you can tell, this is kind of like what? Nuclear plant. And this is, believe it or not, is called what? Hyperboloid of one sheet. We also have hyperboloid of two sheets, and that's coming up next. So just want to make sure that you all see how the general graph looks like, okay? The next one is hyperboloid of two sheets. Notice, contrary to the previous example, all the variables have powers of 2, but now you have 2 negatives. Do you see it? Okay, instead of 1 negative, you have 2 negatives. And the variable which has a positive coefficient, that would be the axis which the sheets will open up. Okay, so once again, you find the cross sections, of the surface with xz plane, yz plane, xy plane. These guys are hyperbolas, correct? Hyperbolas. So is this guy is hyperbola. Okay, but this guy is no cross section. Why is that? Because the sum of two positive numbers cannot be negative. Okay then, so if you would graph your three-dimensional axis, so now you have what? These guys right here, those are like asymptotes, correct? So you have like two of these guys. So there you go. I'm just trying to give you a rough estimation. And then let's say this is like, let's say plus or minus 3. So I'd like to know what would be the cross section of these hyperbolas in what? In so-called in plane, in the cross section of the surface with the plane plus or minus 3. Incidentally, those parabolas, the branches of the hyperbolas will be something like this. Okay, something like that. And now remember, if you replace the z with plus or minus 3 to see how the cross section of the surface looks like at 3 or negative 3, notice I get x squared over 9 plus y squared over 1 equals 5 over 4, which is kind of an ellipse. So what's happening is you get something like this. Okay, and you also kind of get like this. And you also, let me just fix this guy. You kind of get what? Something like, let's say, pardon my graph, guys. So here we go. This is an ellipse. And lo and behold, we have what? Hyperboloid of two sheets. Do you see it? So this is one sheet, right? This is like one sheet, and this is like the other sheet. You see it. So that's called hyperboloid of two sheets. Finally, you have something called hyperbolic paraboloid, which is also known as a saddle. This is a tough one. Okay, you still have what? Z to the first on the left side, but on the right side, instead of these guys being what? Positive, one of them happens to be negative. Question, can you graph Z is equal to negative x squared plus y squared? So the cross-section of this surface with xz plane and yz plane are two parabolas. Notice this parabola right here is z is equal to y squared. This parabola right here is what? Z is equal to negative x squared. So now, if you, let's say, find out what's going on at z equals plus or minus 1, okay, at z is equal to 1, you get what? 1 equals negative x squared plus y squared, which is a hyperbola, okay. The branches open along the y-axis. At z is equal to negative 1, you get negative 1, what? Minus x squared plus y squared. If you multiply both sides by negative, you get 1 minus y squared plus x squared, which is also hyperbola. And the branches open along the what? X-axis. Here the branches open along the y-axis. Anyways, pretend those are the hyperbolas. So what you do, you kind of trace this lower hyperbola like so. And lo and behold, you have a rough graph of what is known as saddle. Okay, so this point is called minimax. If you look at it from top, is minimum. Look at it from the bottom as maximum, so it's called saddle. Alternatively, you can also graph saddle this way. Notice these are the what? Hyperbolas when z is equal to 1, right? Okay, so this is like when z is equal to 1, you get what? Y squared minus x squared is equal to 1, so these are the hyperbolas. And when z is equal to negative 1, you get x squared minus y squared is equal to 1, and these are the branches of the hyperbola, correct? But remember, you also had what? These parabolas, one opening up, one opening down. So if you kind of complete this graph, lo and behold, this would be an alternative form of this, although it doesn't look like it. But some books, they graph the saddle this way. And the way I have learned it is this way, because my professor was also an artist. So he taught us how to graph the saddle this way. Thank you so much.